first speaker is Pavan Kumar from IISER Kolkata. We'll be talking on molecular vibrational dynamics in thermoplasmonic tweezer. So, Pavan, I will give you a warning at 20 minutes.
20 minutes? Okay. Because
at 20 minutes, and then you'll have 5 more minutes.
Sure. No problem.
25 plus 5.
Yeah. Thank you. So at the outset, let me thank Pratap and all the organizers of QMAT for the invitation. And this is actually one of the meetings I always look forward to, and there's a lot to learn for me from attending this meeting. So thanks again for all the organizers. So today I'm going to actually speak some aspects of experimental kind of nanophotonics combined with some questions related to quantum optomechanics. And there is some specific aspects which may be of interest to this particular community, which I intend to highlight going further. So the aspect which we are interested in is to combine kind of quantum molecular dynamics with the optical tweezer platform and ask questions which might be of interest to various different kind of situations. So specifically, I'm going to highlight 2 questions which are of interest to us. First is how do optical and optothermal forces behave at micro and nanoscales? And this is a question which has very wide ambit, and the relevance of this question also is not only in the quantum regime, but also in various different situations, including biology and other kind of scenarios. The second question is more focused towards this particular meeting, and I have kind of explicitly mentioned. And that question is, what can we learn about the structure and dynamics of quantum objects, such as molecules and quantum emitters, using optical and optothermal forces? And if you look at it very carefully, I have explicitly mentioned not only optical forces, but also optothermal forces, because most of the interactions, what we will look at, would have a very strong thermal component to that particular experimental situation. And this makes a very important contribution to various different interaction regimes, which we are interested in. Because most of the experiments, what I'm going to talk about, will be room temperature experiments. But you will see that there are some quantum effects, or rather, I would say, quantum mechanical aspects of molecular interactions, which are quite interesting in some of the situations. So all these questions from a wider ambit actually has a motivation from molecular quantum optomechanics, where one is interested in looking at what happens to molecules when they are constrained by some specific optical interaction, where there can be optical forces and torques, and some very interesting situations can occur because of this interaction. And I'm going to highlight a few of them as I'm going to go into this particular topic. First things first, in order to first understand how do we go about doing these experiments, I need to introduce you to the regimes of optical trapping and tweezing. So if you consider visible and infrared light, which is generally the regime at which optical trapping experiments are performed, the kind of objects you trap can be categorized into 3 different regimes. One is the so-called Rayleigh regime, the other is intermediate regime, and the third one is the geometrical optics regime. These 3 regimes are kind of classified depending upon their size in comparison to the visible wavelength of light. So, for example, the Rayleigh and the Rayleigh regime mainly utilizes the dipole approximation, because the size of the structure which you are trying to trap is much smaller than the wavelength of light. And in geometrical optics regime, you can actually use ray optics situation. And this is something which people have been using very effectively to understand the interaction of light with matter such as biological matter, etc., etc. There is also one intermediate regime which is of very high interest to us, where you have to use full-fledged electromagnetic theory to understand the interaction, where neither the dipole approximation nor the geometrical optics actually comes into picture. And this is the regime which we are very interested in, and you'll see a lot of stuff what we do in our lab is in this particular intermediate regime. However, I should mention that this particular regime, what I'm talking about, can also facilitate some very interesting interaction on either side of the this particular length scales. So the most of the stuff what I'm going to talk in the next few minutes is to actually utilize the optical and optothermal forces in the intermediate electromagnetic regime and try to actually couple them to structures in the Rayleigh regime. This is where some quantum aspects of the interaction come into picture, because this can be understood in classical electrodynamics picture, whereas the structures which we are interested in co-trapping along with, let's say, the plasmonic nanostructures is objects which are essentially quantum mechanical in nature. More so, when we are talking about interactions, I'm not going to talk anything about the atoms, which actually also is a very interesting regime, and a lot of things have been achieved over the past few decades. But of interest to us is the molecular regime. I'm not going to talk about biomolecular regime, because that would actually bring in its own details and interest in a different situation. But we are going to take standard, well understood molecules and their vibrational structure and study their fluctuation in slightly greater detail. So molecular optomechanics has turned out to be an interesting situation to study optomechanical interactions from a viewpoint of quantum objects which are extremely well characterized. You know, this is something which we have to appreciate, that molecules per se actually have a very rigid and specific structure to them, and their energy, ground states, and excited states are very well understood. Therefore, they are excellent platforms to study quantum interactions in various different situations. Specifically of interest to us is the vibrational spectroscopy of molecules in an optical trap, and this can lead to some very interesting spatio-temporal confinement effects, which can be studied in detail in the context of molecular optomechanics. So one of the techniques what we have been studying is the Raman scattering, and many of you probably would be aware of the fact that the optical cross-section of Raman scattering process is very, very low when compared to Rayleigh scattering or fluorescence kind of interaction when it comes to molecules. So this actually brings in its own disadvantage. But in recent years, this disadvantage has actually been kind of negated by utilizing something called a surface enhanced Raman scattering, which is sensitive enough to detect single molecule spectroscopic signatures and also their fluctuations. So I'm just giving you an example of this, this particular interaction, where if you take a specific molecule, let's say a thiophenol or some kind of an organic molecule, and if you take the neat solution at its full concentration, the Raman scattering signal, what you get is what you see here in the normal spectral features. But if you absorb those molecules onto, let's say, nanostructures, then you get enormous enhancement in the Raman scattering signal. And this can be utilized to study fluctuations and also interactions from a reasonably great detail. So I have to mention specifically, this particular technique of enhancement actually has turned out to be extremely important for various different applications in other streams of science, particularly in detecting molecules and studying molecules, and also some specific chemical interactions, catalysis, etc., etc. But that is not the regime at which we use surface enhanced Raman scattering. We are more interested in the electromagnetic enhancement and coupling effects. So what we do is we don't take any complicated molecule. We take simple molecules which have been extensively characterized, but utilize them as a probe to understand electromagnetic effects and also some quantum mechanical effects, especially optomechanical effects in an optical trap, which I'm going to kind of show you in a few minutes. So the focus question related to this particular talk is how to study fluctuations in Raman scattering in an optical tweezer. And the answer is to utilize a single molecule surface enhanced Raman scattering in a plasmonic tweezer, where the plasmonic nanostructure facilitates the optothermal potentials to understand these fluctuations and dynamics. So before I go into this specific work what we have done, I'll give you a very brief overview of the single molecule source. There are two approaches which actually have been utilized historically in this particular single molecule Raman scattering experiments. One is to use one analyte, which means that you are using one molecule at extremely low concentration, and you interact one molecule on an average with one nanoparticle, okay, per nanoparticle. So this actually is a slightly more traditional approach, which actually follows the techniques what single molecule fluorescence methods have been able to utilize. There is another approach which is called as the statistical approach, which uses two analytes. For example, you can actually have molecule A and molecule B, and they are used at a relatively higher concentration. But what happens is during the interaction, on an average, there is only one molecule for a given particular hotspot in the plasmonic nanostructure. Okay, and this changes the game drastically, as you will see once I explain this particular principle. Now, the first approach actually has a very rich history. In fact, it dates back to around 1997, a very famous PRL paper where the surge fluctuation was studied in this particular situation. And interestingly, the statistical distribution of a particular molecule, in this case, a crystal violet molecule, was studied quite a lot. But it happened so that there were some errors in this particular experiment, not actually an error which is intentional, but the interpretation of this particular experiment required a little bit more than just conventional Poissonian statistics kind of an approach to understand this particular interaction. So therefore, one had to actually revisit this kind of fluctuations in Raman scattering because it is not a single molecule which is now emitting the photons, but it is the molecule and the metal nanostructure combined together which actually is leading to this particular emission. And therefore, the statistical nature of this particular interaction had to be revisited. Simultaneously, at the same time, this particular when this experiment was published, there was another very famous paper in Science where people identified that individual nanostructures actually can quench fluorescence and result in very large Raman scattering enhancement. So one of the important messages from this experiment is, if you consider single nanostructures where you have molecules adsorbed to these kind of nanostructures, the fluorescence is much less compared to the Raman scattering signal. Okay, this is one of the prototypical examples of surface enhanced Raman scattering, which tells you that the cross section of the interaction for SIRS is much higher than even the fluorescence signal. So it's an extremely efficient optical process. Therefore, it is used to study single molecule fluctuations in significant detail. So going further, this particular approach was revisited, and a technique called as bianalyte approach was used. In fact, Leroux and Echegoin, two physicists, actually revisited this problem and came out with fantastic analysis of the statistics. They came up with something called as bianalyte technique, where you don't need to detect every single molecule, but rather you will find out the single molecule events. In fact, this is an approach we also take, and this is most of the time the physicist approach, where one is studying single molecule fluctuation in Raman scattering. This is the approach which is now extensively used. There's also another important aspect is that the mixer signal from both the molecules of interest are likely to occur in this particular interaction. And this particular interaction signals from a purely one kind of molecule in contrast of the other. Okay, I'm going to just give you a pictorial representation. But for students and somebody who is interested to look up this very interesting and rigorous methods, I would urge you to have a look at this nice review article and also a very good book written by the same authors, Leroux and Echegoin. So the technique is the following. You have now two different molecules, the blue and the red in this cartoon. So there is when the molecules interact with this hotspot in a trap, there can be di-1 event. And when the red molecule actually interacts with this particular hotspot, there can be a di-2 event. Okay, and now there can be also an event where both the molecules actually participate, which is called as a mixed event. So you actually have both molecule 1 and molecule 2 events, and of course there is another event which is essentially the null event. So what you do is, in this particular interaction for two different molecules, you now have 4 different probabilities or 4 different events and you now track the probability of these events. And if you are in a single molecule regime, you end up getting a majority of the events in di1 event or di2 event. The distribution for mixed and null events are suppressed drastically. Whereas if you actually now take a large concentration of the molecule, the mixed event and the null events actually become more. And therefore, you will actually end up with a Gaussian distribution. Whereas if you now are in single molecule regime, you actually get something called a truncated Pareto distribution. Okay, I'm not going to go into the details of the statistical aspects of it, but if somebody is interested, I would be very happy to discuss. I have some backup slides for later on. Now let's look at how do we approach. The question we are interested in is how to study fluctuations of Raman scattering in an optical tweezer. There are two approaches what we have come up with. One is called as evanescent excitation Raman optical tweezer, where it's an ensemble trapping and tweezing approach. The other one is called as thermoplasmonic Raman tweezer, where we actually push the limits to single nanoparticle. Okay. I'm going to give you a very brief overview of the first one and give some details on the second one. But I'm going to be as specific as possible, so in the interest of time. So one of the important lessons when you actually use plasmonic nanostructure is that when you illuminate these structures, they generate heat. In fact, majority of the light which you incident on them actually is converted into heat. So if you ask what is the heat power density, this actually can be connected to the imaginary part of the dielectric constant of that particular metal. And the incident electric field now actually scales as the intensity and an associated frequency of that particular electromagnetic field. The heat power density essentially is given by this particular formula. Now, the total power absorbed by that kind of nanostructure, if you integrate it over the whole volume, then you end up getting the total power absorbed, which can also be now found out by this particular formula, where essentially the absorption cross-section of the metal times the intensity will give you the total power absorbed. So therefore, importantly, you actually can illuminate a nanostructure and create heat around that nanostructure. What we do is we utilize this heat as an optothermal potential to actually also trap objects. Now, how do we do that? And this we have done it in various different ways. And one of the ways is evanescent excitation, where the experimental technique what we have developed is that you have a prism, and this particular prism is now coupled to a thin metallic film. And now there is a blob of fluid which contains this plasmonic colloids and also the molecule of interest of which you are interested in studying the fluctuations of. Now you eliminate this particular interface with total internal reflection. So remember, this is not a propagating component, but an evanescent component. So therefore, now there is a small gradient of temperature in this particular regime, and this creates a very interesting convective field, and the nanoparticles get kind of trapped in this particular structure. So let me show you the movies of such kind of a trap. And remember, this is an ensemble trap. I will go to a single particle trap later on. So this is an ensemble trap. So if you eliminate, what you see is now an aggregate of nanoparticles getting trapped in a kind of an elliptical geometry. And what we do is we study fluctuations in this particular kind of a trap. So you can see that there's a very large thermal kind of fluctuations in addition to the optothermal kind of excitation fluctuations, which leads to some very interesting situations. Interestingly, you can also play around with this particular potential so that you can now transport this aggregate from one region to other region. There's also a lot of interesting statistical mechanics related questions, which I'm not going to touch upon here. But suffice to mention that we study Raman scattered signal from this particular fluctuating ensemble. And if you study that, you will see that this binary approach can be used. At an extremely low concentration, we recover back the single molecule signatures, what I have been talking about. An important consequence of this is to actually show this extreme statistical distribution, which indicates that what we are looking at is essentially a kind of a truncated Pareto distribution. So this is actually the prototypical extreme statistical distribution, where probability of detecting one kind of molecule in contrast to another kind of molecule is relatively high, whereas the mixed events in terms of both molecule scattering and no molecule scattering is relatively low. However, if you increase the concentration of the molecules, this particular statistical distribution turns out to be Gaussian in nature. Right? It is very interesting to look at this interaction. Now, what I've talked about is all in the ensemble approach. Can we push this to single nanoparticle regime? Because these are questions of interest if you want to really go into purely quantum mechanical kind of effects, of course, at room temperature. Okay, there is still some constraints because you're not working in the vacuum condition, but still there's a Brownian fluctuation. But the mechanical motion of the molecules in terms of vibration spectra is still in a quantum mechanical. So now what we do is we revisit the same equations, whatever I've been talking about. But here also you see that there is this particular total power absorbed can also be equally applied to a single nanoparticle, because you can now take a single nanostructure and look at this interaction. And we now devise also an important strategy where we utilize single metal nanoparticles. And there's also a lot of interesting literature on this, where you can generate heat with this kind of nanostructures. So for example, if you take the total absorption cross-section for a gold nanoparticle, it happens to be so bang in the center of the visible frequency regime. So if you illuminate a nanoparticle made of metal, roughly of the size of 30 to even 200 nanometers, you would end up actually generating a lot of heat from that particular nanoparticle. You can play around with the size of the nanoparticle. And you will be able to now increase the temperature as you go higher in the size for a given particular excitation. You can also play around with the arrangement of the nanoparticle. So you actually can change the temperature in the environment by changing the number of particles which you are illuminating. With this insight, we now devise something called as a single nanoparticle driven thermoplasmonic tweezer. The idea is the following. You actually have a single nanoparticle of 150 nanometer, which is now drop casted on a glass substrate. And now you have a fluid which is now containing the metal colloids, which will further now co-trap the molecules in this particular resin. And importantly, a single excitation at 532 nanometer or 633 nanometer, whichever is of interest to you, at a very low power can now simultaneously trap other nanoparticles, and also it can be utilized to perform single molecule source experiments. And now we look at this interaction and extract statistics from this particular interaction, and we learn quite a lot of interesting stuff. So what is interest to this particular experiment is also the real buoys. So here you will see that we will be able to now trap a small number of nanoparticles, which is tightly confined to a very particular regime. So you will see that this nanoparticle is now illuminated, and this illumination leads to small accumulation of very countable number of nanoparticles. By the way, you actually can see the particles which can go in. By the way, this is actually a specialized optical microscope where we have combined a dark field microscope with an optical tweezer. This is something which we have built in my lab, and we do actually spend a lot of time building optical microscope instruments, especially for tweezing kind of situations. So what we have been able to do is trap the object of interest. You can now study the fluctuations of Raman scattered signal, and then you release them once you switch off the laser, because the particles go back. So you can actually go back and forth. And this is actually the numerical simulation, three-dimensional numerical simulation of the distribution of the temperature in that particular regime. So you can see that the temperature increase is very specific and confined to the single nanoparticle. And also the gradient of temperature actually is also confined to the nanoparticle, which means that you are now creating a small temperature or large temperature difference at a very small scale. And this is the z-axis in which the temperature profile is being projected. Now going further, we actually
Pavan,
yes.
You have 3 minutes.
Yes, I'm done. So you can also study this fluctuation in a specific way. You can look at the same fluctuation signatures. The noise can be studied in significant detail. It's a very beautiful kind of a situation where the fluctuation in the signal actually can be utilized to extract some important information. And if you go very deep into this noisy regimes, you can also learn a lot about the fluctuation dynamics in such situations. From that fluctuation, you can go further and extract the eigenvalues, and you can recover back the single molecule data, whatever I've been talking about. What is of interest to this community probably is also the regime in which you can trap single objects. So you actually can study fluctuation between two objects. For example, here is a nanoparticle which is being co-trapped on another nanoparticle. So you have a single nanoparticle trapping, and as long as the laser is on, the trap is actually active. So you can study fluctuations in such kind of, you can not only study fluctuations in the spectral regime, you can also study the fluctuation in the spatial and the temporal regime, which is of interest to various different situations. So you can also transport this small fluctuating stuff. For example, if you can create a small aggregate of this kind of colloid, and this, by the way, they are all co-mixed with molecules, so you actually can still study the spectral fluctuations in such situations. So you'll see that having trapped this small aggregate, you can now transport them in. So you can see that we are transporting the small stuff, and we can transport them down. It now comes down, and now having transported them, you can release them back in any place. So you actually can do this on any device also. For example, you can do it in even two-dimensional materials and other kind of structures. And here what we are showing is glass, and this is a experiment which is done using 633 nanometer laser. Now we can play around and achieve this in various different situations. We actually can also add some specific molecules which actually can lead to some very interesting oscillatory signatures. We can also play around with the larger particles where you want to replace this, for example, with a slightly bigger metallic nanostructures. You can also push it to regimes, for example, a nitrogen vacancy diamond kind of nanodiamonds and things like that. One actually can be utilize this platform to do multiple experiments where you can study fluctuations, where you have spectral and its spatial and temporal fluctuations all recorded simultaneously on one particular platform. So we have constructed a kind of series of experiments to ascertain this particular principle. And I should remind that this is not a commercial microscope system. Actually, we have built this system over the last almost a decade. So there's a lot of effort. I should really thank my students for that, for building these techniques in the laboratory. So finally, I'm going to tell you that we can also utilize these plasmons not only to trap objects, but you actually can create a kind of an interesting pulling forces. So for example, the forces what you generate in such kind of regimes, in this case, a dielectric colloid has been pulled to the excitation point. So you can see that you can study some specific friction aspects of a single object being pulled due to the electromagnetic, or rather surface electromagnetic waves on this. Interestingly, there is a very strong polarization dependence. You can study crystallization of colloids if you have your polarization along the length of the wire. Whereas if you switch the wire to the in such a way that the polarization of excitation is perpendicular, you get trapping, but no two-dimensional assembly. So which means that you can study a kind of out of equilibrium nucleation, aggregation, and growth of crystals in a visual manner using this particular experiment. So to conclude, what I've asked is a question of how to probe vibrational fluctuations of molecules in nano-optical tweezers. I've given you kind of an overview of different regimes in which our experiments can be performed. An evanescent regime, or also in a single nanoparticle regime. We can also use nanowires to actually create quasi one-dimensional interactions. We can also create quasi two-dimensional interactions where you actually can study two-dimensional crystal formation because of an optothermal defect. This is something I did not discuss in the talk, but this is also an equally interesting regime where you use a single crystalline nanostructure and you excite this evanescently, and you create a two-dimensional crystal. And it's a very interesting way of studying kind of formation of two-dimensional crystals under perturbation. So all this would have not been possible without the support of my students and their effort of my students. Sunny Tiwari is the instrumental person behind all the single nanoparticle trapping experiments, ably assisted by Vandana Sharma and Deeptharata Paul, and other students have also played. That's the reason I show all the names, because as you know, in lab, everybody's help is very important. Former students, Partha was the one who initiated the evanescent wave trapping experiments. And also my MS students, Rohit and Utkarsh, also played a very critical role in building some of the instruments what we have kind of developed in the lab. And thanks to also the funding agencies. And most importantly, to all of you for coming up, for coming to this particular talk on a Saturday morning. And thank you all for your attention.
Yeah. Okay, thank you, Pavan. So we have time for a couple of very quick questions.
Yeah, sure, please.
So are there questions? I don't see a raised hand. So in that case, let me ask you one thing.
Yes.
Pavan, so these experiments are all at room temperature. You mentioned that.
You're right.
Is it possible or easy to make a temperature variable stage and study these?
Yes. Actually, a very important question. It is relatively easy to go higher in temperature, because we are devising techniques where we can go even higher in temperature and look at things which can happen at, for example, if one is interested in phase transitions and things like that, one would be also able to do this down to the liquid nitrogen temperature. Of course, in the appropriate fluid, then one can actually perform this. But the techniques what we have developed is general, in the sense you can actually also have an optical window in a cryostat and then perform these experiments where you can create such structures and assemblies in vacuum. That is also equally possible. In fact, there is no reason why we cannot go to that regime. But that would actually add one more layer of complication. But it's very much feasible. Of course, there will be no Brownian fluctuations there, or minimized Brownian fluctuations. One would be able to do this. People have been able to do this where they are studying this levitated dynamics of structures in an optical trap. And there are some very interesting questions related to even nonlinear dynamics of objects in such traps. But we are also now looking at mainly the room temperature aspects, because there is quite a lot of interest for biologists and also soft matter kind of research. Because a lot of tools what we have developed over the years can also be utilized in vacuum conditions in principle. But that would just lead another level of complication. That's all. Yeah. In principle, yes, the questions can be addressed in that.
Okay, Pavan. Thank you very much for a very nice talk. So
I'll stop to sharing.
Yeah.
Thank you. Thanks.
We move on to the next presentation, which is by Professor P Bhallmudi from IIT Madras. And he will be talking on magnetic spectroscopy using quantum defect in diamond. Over to you, Vita.
Thank you, Pratap, and thank you to the organizers for inviting me and giving me a chance to speak about my work. So I'll be talking about spectroscopy using some quantum defects in diamond. And so I'm from IIT Madras, which I joined 2 or 3 years back. We are establishing our lab. And so a lot of the work that you'll be seeing here is still done in association with my former lab in collaboration with Professor Chris Hamill's lab. And so the outline of my talk will be, I'll first introduce the particular defect center of interest to us, are the nitrogen vacancy centers. And I'll be discussing how we do spectroscopy using them. The first example that I'll be discussing about is demonstration of ferromagnetic dynamics. And so then how we understand them in terms of spin relaxation based mechanisms. And this is in contrast to a lot of people use these defect centers as using coherent manipulations of the defect centers to do magnetometry studies. We will be using spin relaxation based methods. And then I'll sort of show some multi-magnon processes that can help in extending the range of the spectroscopy. The second example that I'll be discussing is paramagnetic spectroscopy using these NV centers, where I'll be showing the experimental observation. We don't fully as yet understand the mechanism by which this is happening, but as an experimental tool, it's quite interesting. And one of my students has been working on doing some simulations of these quantum systems to shed more light. And he had in fact presented a poster on the subject. So I'll be giving a brief overview of that also. And so later, time permitting, I hope I can show some of the other work that we are getting into in our lab here at IIT Madras in terms of photon sources using diamond. And so I should thank, because usually we run out of time at the end, so I should thank all the people who have contributed to most of the work that you'll be seeing, primarily from the group of Chris Hamill, and of course now most of these students and my collaborators in various other institutions and other places, and there are many other collaborators that I should thank. And so I should give you a quick introduction to nitrogen vacancy centers in diamond. And the basic, I'll give a big picture overview of why people are interested in these kind of centers, and not just nitrogen vacancy. Nowadays, there are many different kind of quantum defects that are emerging, and not just diamond. Within diamond, there are many defects like silicon vacancy, nitrogen vacancy, even in other materials, 2D materials, and many other places. They show some quantum behavior which can be used. And in our case, the reason why we are interested in them is first is for building sensors. And these can be very powerful sensors for the nanoscale, reaching, I mean, people have been able to reach atomic scale, or at least, approaching nanometer scale resolutions. So that is one of the things. And you can use them in ambient conditions and at room temperature. So for biologists, it's quite a bit of interest from that point of view. I'm trying to find my laser pointer here. And so sensing applications, people are concentrating on quantum computation and registers. Again, I won't be able to cover all of these in detail, of course, but just to give idea for people of what is of interest to them. And another big source is light sources. These could be single quantum emitters or building lasers or masers. So I'll be discussing a few of these things. And most of these we can understand from this energy level diagram that I'm showing for the NV center. And when I say NV center, I should be careful, and I won't be saying negatively charged NV center, but that is the one of interest. That is the one that shows this nice spin triplet energy that has a spin triplet in it. And this is the energy level given for it. And so I won't keep saying negatively charged NV center, but that's what I mean for this talk. And so the energy level diagram, of course, there are the orbital levels, which give you the ground state and the excited state. And as I said, the negative charge along with the nitrogen, which provides one extra electron, they both together form a triplet pair. And this spin triplet enables these very nice applications that we'll be looking at. And so the basic idea is that you can shine laser and you can, of course, get a fluorescence. The fluorescence is of the order is in the red, somewhere between 600 to 800. The spin triplet has a zero field splitting of about 2.87 gigahertz. And of course, if you apply a magnetic field, you can split the plus and minus 1 levels. The interesting thing that happens is that there's an interstate crossing via singlet levels here, which can allow you two things. And for this talk, that is all you need to, I'll just focus on telling you the two interesting things that happen. First is that the spin state can be monitored by measuring the fluorescence, okay? So spin 0 is bright and plus and minus 1 are going to be dark. And similarly, the other thing that follows from this is that if you do a few cycles of this optical excitation, you will initialize the spin state to a very high degree into the spin 0 state, much higher than what can be usually achieved by thermal means. So all of this means that you can detect single spin at room temperature and in ambient conditions. And what I should have listed here and what is not listed here is that the spin lifetime actually happens to be rather long because this is a nice quantum object sitting in the middle of a diamond lattice. And it can be, you can design it so that it can be fairly well isolated. And so that long spin lifetime also plays a big part in the applications. But the key idea of all of this is that you can do magnetic resonance, which is basically just manipulating the spin states. And you can monitor that by simply looking at the fluorescence intensity. And you can do what is called the optically detected magnetic resonance. And now by monitoring the changes of this magnetic resonance, either be it shift of frequencies, which would be in the case of coherent manipulation, or by measuring the changes of the lifetime, which is related to the line width here, you can say something about the magnetic fields being experienced by the spin. And that's at the heart of a lot of what you're going to see. And of course, the light applications that I'm talking, you can think of this laser here. These optical levels can be used for doing single quantum emitter kind of applications. And then later on, we'll also be looking briefly at maser applications, which will be given due to these microwave levels here. And so let's discuss about the spectroscopy. And so the spectroscopy is going to be given by the ferromagnetic spectroscopy that we are discussing. And the basic measurement that we are going to be talking goes something like this, that in this particular case, I have, let's say, a ferromagnet, and I'm going to put some nanodiamonds actually. And so these nanodiamonds have NV centers in them, and you can just drop cast them. And we are doing a magnetic resonance experiment where we'll be applying a magnetic field and there'll be microwaves. But the readout is not, unlike the conventional inductive measurement, we'll have a fluorescence measurement. And so we'll have a lock-in measurement where we modulate the microwaves and we can do the measurement. One thing to notice, so what we typically will see are these field frequency maps that we'll be generating. So we have the magnetic field and we have a microwave frequency, and we can sweep through both of those and we can generate these field frequency maps. And the key thing that I'll highlight is that when you put it on a ferromagnet, you're going to see a very nice change of the fluorescence, which we have confirmed through other control measurements. We can discuss them later, is the change of spin state of the NV center. And this matches with the ferromagnetic resonance condition. And when we first saw this was a big surprise to us, at least the intensity of it was a surprise to us. And this is because the NV seems to be responding far away from its own resonance. And I should point out these other features that you're seeing. This is the ground state resonance of NV centers by themselves. These the excited state resonance. But the NV seems to respond quite far away from its own resonance. And you can see this with that was with a canonical ferrimagnet YIG. We have been able to see it with even in an organic ferromagnet, VTSCNE, and other metallic ferromagnets as well. And so we have confirmed this in different materials. Here we had a single crystal diamond on which we grew this VTCNE film. And once again, you can do the same thing. You can very nicely map out the FMR of this ferromagnet. But again, this is now a local measurement. You are able to measure FMR on a scale that is given by, let's say, in our case, the spot size of our spot size of our optics, of our laser beam. But in principle, you can also go down to a single NV level. You can do the measurement with so you can do the measurement fairly locally. And so the way we understood finally is we could do some spin relaxation measurements. So in this case, what we are doing is we are polarizing the NV spins using laser beam. And so after polarizing, we wait for a certain amount of time and watch the spin come back to equilibrium, during which time we are applying microwaves we can apply the microwaves at the FMR frequency. And what we see is that as we apply microwaves at the FMR frequency, we are seeing a change of the lifetime of the spins, of the NV spins. And so the way that means is that, first of all, FMR itself is not at the NV resonance. So we must be creating fluctuating fields at the NV resonance itself to cause relaxation. And so we could verify this again by doing so. In the interest of time, I won't belabor too much on this part. I'll go to the next part. But the main idea is that we can do, even in the absence of microwave excitation of FMR, we can do some spin noise measurements. And we could do by varying the space relative to the ferromagnet. So we could create this wedge structure, and we could change the distance between the NV centers and the ferromagnet. And we could fit it by modeling to the spin wave spectra created by the ferromagnet. And so we could do all this, we could verify all this, and I'll come to the punchline here probably, that will be the best thing, is that the way we understand is that when we are driving the FMR on its resonance, we will have a thermal spin wave. So the FMR itself decays by scattering off of thermal spin waves, and these together will then give you a spin wave that is resonant with the NV centers. And by doing this, we are able to sort of generate the spin waves that are resonant with the NV centers and relax the NV centers. And by doing that, we can perform FMR That's one thing. And the other thing that we are also looking forward to is using this as a way to study ferromagnetic relaxation, which is normally not that easy, but we are hoping that this can provide a tool for studying spin wave relaxation. One thing for people who have, if you have followed, is that if this FMR goes above this range here of the NV, this mechanism will not work anymore. But as it turned out, when we did these measurements at higher powers of microwave, so when we did this at higher powers of microwave, here, if you notice at higher powers of microwave, we see that this region where we could do the detection is being extended. And so this again, we thought we should understand. And the way again, what we can see is that there are two actually effects happening. One is that the peak where the NV response is not quite at the uniform mode at higher powers. You can see that it slowly moves away from the uniform mode FMR. And the other is the extending of the range here. And both of these are related to instabilities that are creating. So we are creating some Soule instabilities, or these are basically high power regimes. So we are doing some parametric excitations of high K magnons. And so these are two magnon processes that can give you basically high K, these non-zero K magnons. And those are what are now being scattered. And that is what is giving us this. So those are being scattered to be resonant with the NV centers. And that's why the NV frequency shifts away, because these have, see, again, I should point out that if everything is uniform, if it's 0K, a uniform magnetization will not create a magnetic field at its center. So what you need is some fluctuating magnetic fields, and that's why we need these non-zero K magnons. And those are what can couple to the NV centers, and that are what is being created here. But the other way we can also see is that when you cross this ferromagnetic gap here, so let's say the NV was sitting in this gap here, you could still have a process, a 4-magnon process, where the thermal wave and the driven wave are creating two magnons. And the difference of these magnons now can match the NV centers. And that again can sort of relax the NV centers and give us the spectral signature for the ferromagnetic resonance that you can sort of measure here. So these, so we have been able to, so the short thing that I would summarize there is that we have been able to measure FMR, and we are finding ways of extending the range of doing this FMR spectroscopy. The next one that I'll be looking at is paramagnetic spectroscopy using NV centers. And what we see here is again an experimental observation that these are P1 centers, and that we are looking at. P1 centers are substitution nitrogen centers. So when they combine, I sort of realized just now that I had never actually highlighted what the NV center was. I should have pointed out that the NV center is a nitrogen vacancy coupled with a substitutional nitrogen. That is what an NV center is. And I apologize for not setting this in the beginning itself. And so the P1 center is the substitutional nitrogen center that you have. And so you can have a coupling between the NV and the P1 that you will see. And we again have been able to do this spectroscopy where we are driving at the P1 resonance, not at the NV resonance. And we are able to see the hyperfine structure of the P1 center. And we can verify that this is indeed the P1 center by looking at the hyperfine spectrum. And so we have been able to do this under different conditions, whether the whether the magnetic field is parallel to the NV centers, or it could be predominantly perpendicular, which is along the 100 direction, not exactly transverse, but more or less transverse to the NV center. And the advantage of doing something like this is that most of the NV techniques for doing magnetometry require you to have a field that is oriented along the NV axis, which is its quantization axis. So they require, the coherent manipulation techniques require you to be oriented along the NV axis. But in this particular case, we don't need such constraints, and we are able to measure so we can measure the anisotropic hyperfine spectrum of different paramagnetic species. And so that's one of the advantages of this technique. But we can show that this can be again applied in a broadband spectrum. We have done it in nanodiamonds, we have done it in, which is a powder spectrum. We have done it in single crystals. And so we have been able to again show broadband spectroscopy. And the thing though is that in this case, there are no spin waves. So there is no matching of the spin waves. There's no decay of the paramagnetic spins into a spin wave that can match the NV spectrum. So we are still trying to understand what is happening. And so my student Anshuman has been doing some simulations to try to understand the coupling of the NV centers with the P1 centers. And so we can write the Hamiltonian. So we could write the Hamiltonian for the NV and the P1, which is a simple dipole coupling here. You can, of course, have the Hamiltonians for the NV themselves and the P1 themselves. And so you can do all of this. And when we do all of this, we can sort of understand how the NV and the P1, first, the simpler case where the NV and the P1 are resonant to each other, which is easier to understand. And so we have been able to verify that our model works. And in this case, predominantly, in this particular case, I think is restricting his simulations to be between the NV and the -1 levels of the P1, I think, or the P1 and the NV, where the NV levels are restricted to 0 and -1 sublevels. That's what he's looking at. But the main thing is that we find there's a flip mechanism that allows you coupling between the two spins. And in this particular case, because the resonant frequencies match, we see some coherent oscillations, and sort of we can find the usual 1/r³ dependence. And we find that basically we can verify our simulations are working nicely. And based on that, we are now applying them to understanding the spin dynamics where the NV and P1 are off resonant to each other. And we are able to verify in the simulations that we can see a change of the NV spin state as we apply a microwave, as we are driving the P1 centers. But this is still work in progress. We still haven't figured out a full physical picture of what is happening. And so we are sort of working, but hopefully by the next time if we talk, I mean, we should have a better idea of what is happening. So, but this is sort of where we are headed in trying to understand this paramagnetic signal.
Vidya, you have 5 minutes.
5 minutes. Okay, that's good. So I did rush through. Hopefully I didn't lose everybody. So I'll try to wrap up in the last 5 minutes with some of the work that we are doing now is in understanding or building light or photon sources. And this, I should say, is very much work in progress. The pandemic has, of course, not helped experimentalists, especially those who are setting up their labs. And but we have made some progress, and I would want to show where we are headed. And so one of the things that we are doing is looking at building towards a maser. And so there's some nice work people have been doing in trying to build masers using NV centers. Masers were, of course, built before lasers, but there are practical difficulties because the energy level separation is so small compared to room temperature for spin levels, which are typically needed for maser transitions. And so because of this, there have been difficulties in building room temperature CW maser. But as it happens in NV, if you apply a large enough field, this triplet -1 level can come below the 0 level. But now you can initialize the spins at the 0 level itself using this laser pumping that I said, which means that you can create a population inversion. Okay, and this population inversion, again, coupled with the idea that we have long spin lifetimes in NV, makes, and the fact that NV is a very good thermal conductor, so it can dissipate all this laser pumping power that you're putting in. It makes it ideal for generating towards building maser. And so we still don't have a maser as yet in our lab, but what we have done is the first step towards an important step, which is showing the inversion of the population. And so we have been able to create this inversion of the population. This is work done in a conventional EPR cavity. So we are doing these measurements, EPR measurements, and so this is standard EPR measurements, but now we are doing it while applying the laser and without the laser, which is this dark spectrum here. And this is 5 times multiplied already. So the spectrum is much smaller. As you can see that we get a huge signal when we apply the green laser and polarize our spins, and also the sign inverts for the 0 to -1 transition. For the other transition, it does not invert. So we can create a spin inversion. We have been able to verify it, and we are in the process of studying this signal more thoroughly, and we are hoping to wrap this up work soon, but this is where we are presently. And what I'll end with last is we are also trying to build towards single quantum emitters. And so in this particular case, we are taking advantage of the fluorescence, a nice stable fluorescence. And so these typically can give you quantum emitters. People have demonstrated this. The engineering challenges are that you need diamond has very high refractive index, so extracting light out of diamond is a bit tricky. And so people have come up with a solution of using these nanopillars. And so we have started building these nanopillars. These are made out of FIB. So these are just early days. We are starting to build these photonic structures, and we are hoping to build upon this and sort of look at single quantum emitters shortly in the future. Okay, with that, I will come to the end of my talk. And so the key points I want to highlight is that we looked at quantum relevant defects in diamond, and these have excellent properties, mainly that spin and optics are combined, which enables you very sensitive detection of spin state. These have long spin lifetimes, and these enable long nanosensing applications. And then we have demonstrated relaxation-based modality for performing ferromagnetic spectroscopy, and most likely the paramagnetic is also in some way related to some kind of relaxation. We are trying to figure that out. And the NV centers can be useful in developing masers and single quantum emitters. So hopefully I've given you a broad overview of what can be done with these quantum emitters. If you have any questions, I'm happy to take them. Thank you.
Okay, thank you for a very nice presentation. Now the session is open for questions.
Let me see.
I have a question.
Sure.
Yeah.
Hi, Pavan.
Yeah, Praveen. Nice, very nice talk, Praveen. And regarding this confinement in the context of these photonic structures, what you mentioned. So, would you also observe something where you can go other way around, like inhibition of spontaneous emission, and it can trigger some new selection rules and things like that? This is very interesting, because maser is a regime which well, historically that was the first one which was achieved before the laser itself. And I'm just curious, because during that work, people have observed that there is a change in selection rule. And I'm just wondering whether such kind of situations also exist in your experiments.
We have not as yet reached that regime, but that's kind of what we are trying to. I'm not sure maser, it'll be engineering will be a bit more we are working towards, but okay. Even with the single quantum emitter, yeah, I would be curious in looking at the effect of polarization, what kind of whether we can confine and whether we can look at these photonic structures. Nice. For the maser, we have not as yet started building metamaterials, so to speak, or something to engineer that, but that's sort of in a bit longer term plan that is there.
Yeah, so because spectral signatures would surely be very fascinating in such situations.
Exactly, and that is the key. That is one of the key things. Both for us right now, it's a bit tricky because I have to control my NV center orientation, which is a big challenge right now in the growth. And so that's a materials aspect we are working on separately with other people. And so we are trying to develop control on the NV center, because ultimately I need to control the dipole, be it for the optical one or the microwave one. And so that's one of the challenges, but that's where we are headed. And once we have those kind of controls, I'm hoping I can answer that's exactly the kind of questions that I'm interested in answering. And I'm hoping that we can work towards that.
Thank you. Thank you.
Thank you for that question. Yes. Okay.
Okay, I have a small question. So,
yeah, sure.
It's a general question. In terms of this NV center-based magnetometry,
yes.
How does it? What's the state of the art now? How does it compare, for example, with squid magnetometry?
So, so it's extremely good. I don't have the comparison graph. Normally there's a plot I can show you about spatial resolution versus sensitivity. And usually in that graph, the NV would be sort of approaching very good. And the state of the art is people have, let's say, done recently, people at Delft University, Tien Miao group, they did 27 atom imaging using NV centers. So these are nuclei inside the NV. So you're actually mapping nuclei using the NV centers. So this is the state of the art for nanoscale MRI. And so in that sense, and this is being done at room temperature and in ambient conditions. So in terms of if you combine the idea of working conditions, I think nothing comes close to it. In terms of sheer sensitivity, NV centers have not reached, let's say, surf magnetometry with atoms that they do with atomic electronic nuclei that people do. But we are approaching fairly close, but those are for bulk sensors, not for nanoscale sensors. For nanoscale sensors or atomic sensors, I would say that I doubt if there's too much competition right now.
Okay, so thank you for a very nice talk. I
Okay.
think we'll move on to the next speaker now.
Cool. Thanks again to the organizers. Okay, I'll stop sharing.
So the next speaker is Abhishek Nag from Paul Sherrer Institute, and he will be talking on detection of acoustic plasmon in hold-up lanthanum and bismuth cuprate superconductors using resonant inelastic X-ray scattering. Okay, so over to you, Abhishek, and I will give you a warning at 10 minutes.
Yes, thank you. Yes, hello. I would first like to thank the organizers for giving me this opportunity to present our work here. And I really congratulate them wholeheartedly for successfully organizing yet again a conference of this scale during these difficult times. I'm currently a postdoctoral fellow at Paul Sherrer Institute with Professor Steve Johnson, but this work was done at Diamond Light Source, where I was working with Dr. Keijin Zhu. And this work involved several groups whom I would like to thank. And our group at Diamond Light Source, where all the experiments were done, Donjun and Hiroshi from Japan, who grew some of the single crystals, Stephen Hedden's group from Bristol University, who grew another sets of single crystals, and Matthias and Andres from Argentina, and Yuki from Japan, who did the theoretical calculations. So let's begin with the well-known Cuprate phase diagram that originates from doping of electrons or holes into the antiferromagnetic charge transfer insulators. As you can see, despite subtle differences in the various orders, there is also a significant amount of similarity between the electron and the hole dope sites. So to understand the different phenomena in this Cuprate phase diagram and to eventually understand the origin of superconductivity, scientists are looking for low energy bosonic excitations that can couple to the charge carriers. Now, the primary bosonic excitations that have been identified to play a significant role in the pairing mechanism are the phonons or the lattice vibrations, or the magnons, the spin excitations. Now, in metals, there can be another type of collective excitation called the plasmons. And these plasmons were predicted by David Pines and David Bohm in the early 50s as the quanta of collective charge density oscillation arising in the presence of long-range Coulomb interactions. And plasmons play a very significant role in the screening of electromagnetic fields and therefore in the optical response of materials. As a simple example, this cup reflects or transmits light of different colors depending on the different resonant frequencies of the gold and silver nanoparticles that are embedded in it. Now, there can be different types of plasmon modes depending on the charge density distribution. For an isotropic charge distribution, the plasmon energy has a quadratic dependence and a finite cap at low momentum. In contrast, when the charges are confined to 2 dimensions, the plasmon energies can be made to go down to 0 energy. In the cuprates, however, which have a layered structure, the doped charges reside in the copper-oxygen plane. And this creates a periodic array of layered charges separated by dielectric blocks. Therefore, we have an intermediate situation where the charge oscillations in the different planes can give rise to plasmonic modes, which tend to go to 0 energy at small values of in-plane momentum, while for certain out-of-plane momenta, one can observe optical plasmon modes which have energy gap. And these plasmon branches appear due to the interplay of the interlayer Coulomb interactions in these materials. So naturally, after the cuprate superconductors were discovered, several theoretical works proposed that such low-energy acoustic plasmons in presence of coupling with phonons could also contribute to superconductivity. Unfortunately, such low-energy acoustic plasmons were not observed for over 3 decades in the cuprate superconductors. The breakthrough came in 2018 when Wei-Sheng Li's group from Stanford University discovered the presence of acoustic plasmons in electron-doped cuprates using a technique called resonant inelastic X-ray scattering at copper LH, A following work, again using copper-alleged rigs, showed that the doping dependence of the plasmon energy did not follow the expectations of a free electron model, which is a clear indication that the plasmons carry the effects of the electron correlations that define these cuprates. Surprisingly, in the hold-off cuprates, which were much more widely studied using copper-alleged rigs, there was no indication of such acoustic plasmons. So the character of the low energy charge fluctuations becomes questionable across the phase diagram. Why should the hold-off cuprates having similar layered structure not have such low energy charge fluctuations? Could it be that the on-site correlations are very large so that the fluctuations are suppressed and confined to a very small region? Or could the long-range interactions be so weak that these excitations are below the resolving powers of the experiment? Or could it be the combined effects of the on-site, the intraplanar or interplanar Coulomb interactions that drastically modify these plasmons? So let's first take a look into the Riggs technique, which was used to observe the acoustic plasmons in the electron-doped cuprates. Here, an incident X-ray beam knocks off electrons from the core orbitals of the atoms and excites them to the empty valence orbitals. Now, if one monitors the amount of X-rays absorbed in this process, one gets an X-ray absorption spectrum. Now, because of the hole in the core orbital, the state is extremely unstable, and therefore electrons from the occupied orbitals can fill up this hole, and this effectively creates an excitation. If one then detects a X-ray beam that is emitted by this de-excitation process, one sees that its energy is smaller than the incident X-ray beam by an amount that corresponds to this excitation. So one can probe different element-specific excitation using this spectroscopic technique, Riggs. And Riggs has been used extensively to study superconducting materials. One of the early important works found the presence of charge ordering in yttrium barium copper oxide, apart from orbital and magnetic excitations. And then Riggs was also used to study the doping dependence of magnetic excitations across the cuprate phase diagram, providing key insights. With the development of the Riggs instrumentation, it is nowadays possible to study excitations in the extreme limits of the modern day materials. For example, you can see here magnetic excitations in a monolayer, or basically an unit cell thick of iron selenide using iron-alleged Riggs. So it's quite obvious that the recently discovered nickel-edge superconducting thin films that Professor Tanushree Shah Dasgupta described in her talk this morning would also be studied using Riggs. Using nickel-alleged Riggs, a clear evidence of hybridization with the rare earth element was observed in these superconductors, which is absent in cuprates. And although the magnetic ordering in these nickel-edges are, still under debate, this year we observed that significantly strong magnetic excitations are present in the parent and the superconducting nickel-edges. And just this week, you may have seen 3 articles have been posted on arXiv demonstrating the presence of charge ordering in these systems using Riggs. Now, I should mention one thing, that these magnetic excitations, the degree of nickel rare earth hybridization and the charge ordering largely depend on the presence or absence of the capping layer that is used to protect this sample, although this does not affect the superconducting properties. So in the coming years, we'll see the story of nickel-edge superconductors unfold, and definitely Riggs will contribute heavily to the experimental side. Now, coming back to the cuprates, as we have seen in Riggs, we can choose the elements selectively in a system. Since spectroscopically at the copper edge, we probe predominantly the upper Hubbard band, and the doped holes in these systems go primarily to the oxygen orbitals. We thought, okay, let's investigate these systems using oxygen KH Riggs. So we did incident energy dependent Riggs across the whole peak of this cuprate lanthanum strontium copper oxide, LASCO. And as we can see, there is one peak that has a non-Raman behavior and a sharp peak at around 130 milli-electron volts that almost does not change in energy as the incident energy changes. This suggests that this peak has a coherent nature, unlike this high energy peak. So we started looking the momentum space propagation of this sharp peak. And as you can see here, this sharp peak disperses towards the zero energy, much like the acoustic plasmons. We did the same scan for another family of cuprates, the bismuth-based single-layer cuprate, which is commonly termed as BISCO. And again, we find similar sharp dispersing features in the momentum space. Now, since all the excitations in these layered cuprate systems are two-dimensional, whether or not these are really acoustic plasmons can only be confirmed from their interlayer character. So we probed along the outer plane directions, and we again see this dispersion of this peak in LASCO. In this single layer cuprates, however, you have a copper oxygen plane in the middle of your unit cell. So the periodicity in the out of plane direction is not at 1, but at 2. But with LASCO, we could probe only a very small region. So that's why we chose BISCO also, which C-axis lattice parameter is almost twice that of LASCO, so that we could probe a much larger range of the momentum space. And here again, you can see that this mode disperses quite a lot in BISCO. Now, if you ignore the energy differences for a moment, you can indeed visualize the dispersions of these excitations in the out of plane direction with a periodicity that is expected for the acoustic plasmons. Now, since the cuprates are strongly correlated electron systems, it was interesting to compare our results with the recently developed calculations of plasmons in the framework of a TJV model. And here our collaborators included a three-dimensional form of
Abhishek,
the long-range.
you have 3 minutes.
Yes, thanks. Three-dimensional form of long-range Coulomb interaction to calculate the dynamic charge susceptibilities. And if we plot the extracted plasmon energies from experiment and then we compare the dispersions that we obtained from these model calculations, we see a very nice match for both the materials, further confirming that we are indeed observing acoustic plasmons. And as you can see here, the plasmon energies do not exactly go to the 0, but there is a finite gap present. And this is due to the interlayer hopping interaction that is included in the theoretical model. And this gap should be much enhanced in the infinite layer cuprates where the interlayer spacing is much smaller. You can find more comparison of the theoretical results and the experimental results in this work that was published last year. And but before I stop, the one thing that I want to highlight is to by showing how sensitive these charge fluctuations are to the interlayer properties in these systems. So as you may have already noticed that at L equal to 1, the plasmon energies in BISCO is much larger than LASCO. Now, if I plot the ratio of the Coulomb interactions between BISCO and LASCO in the HL plane, just using this formula basically, I get a map kind of like this. And then if I use analytical forms of the plasmon dispersions from, say, RPA model, and then I plot the plasmon energy ratios between the BISCO and LASCO again, I get a very correlated map with the Coulomb interactions. So it is very clear that the plasmon energy dependence is strongly modified by the amount of Coulomb interaction, which in turn is determined by the d-spacing of these interlayer separation in these cuprates. Because the interlayer spacing of BISCO is larger than LASCO, that's why the plasmon energies are larger in BISCO than in LASCO. So to conclude, we have demonstrated the presence of acoustic plasmons in two families of hold-up cuprates, therefore kind of restoring the balance in the cuprate phase diagram. And these plasmons are strongly dependent on the interlayer interactions and have a strong oxygen on-site character, unlike the electron-doped cuprates, despite the strong copper-oxygen hybridization. So the perception that in-plane charge fluctuations are strongly suppressed by Coulomb interactions is not correct for these systems. And further studies can lead to the understanding of the potential differences from the electron-doped systems, along with their interactions with the different bosonic excitations that are already discovered in these materials. And at the same time, presence of acoustic plasmon in hold-up cuprates opens up a large number of possibilities for exploring them in bilayer or tri-layer systems, or in the context of the different phases in the cuprate phase diagram. And I will stop here, and I thank you all for your kind attention.
Thank you, Abhishek, for a nice presentation. The session is now open for discussions, questions. Okay, I have a question. So, when you show your data for the dispersion, these peaks look very broad, means not these, but the colored plots. Yeah. So when you see, when I look at the colored plots, other than the sharpish peak, you have a very large, it seems, incoherent background. Why is that?
So there are two things. One thing is that, yes, these peaks are much broader. I mean, if you just compare this with, I quickly go to the electron doped cuprates, these +1 peaks here are much more sharper.
Yes.
We are currently looking into this. We probably think it has to do with the difference in the correlations, on-site correlations, that is different between the hole doped cuprates and the electron doped cuprates, which introduces this additional broadening of the plasmons in the hole doped cuprates. So that is one thing, one part of your question. The other part you asked is you see there is this broad kind of feature. This is, I think, what you were asking. So this feature is basically this feature that you see in the incident energy. This is quite broad. And this feature appears from the bimagnons excitations in these systems. So at oxygen kh, you can also excite bimagnons, and these appear at these energies. So this is present, but this is mostly non-dispersing, which should be the case for the spectroscopic signature for the bimagnons in these systems.
I see.
I have a question, Abhishek.
Yeah.
It's a very nice talk.
Yeah, thanks, Robert.
And the point is, it's a nice question. For the electron doped cases, the data that you showed, which age was probed in that?
It was probed using copper LH.
And
but
in this case, for the hole doping, you actually used oxygen age, as I see. Don't you think you cannot do it by copper age?
So let me show you some other results. So in the hole doped cuprates, we use this copper LH data, exactly the same geometry. We find very faint kind of excitations. I mean, if we had not probed the oxygen cage, it would be very hard to believe if there is something really here.
And why is it so?
One argument is that because mostly the doped charges, they go and occupy the oxygen orbitals, it might be that the charges are more oxygen-like, but it's difficult to really understand because you have very strong copper-oxygen hybridization. We have also probed both copper and oxygen for the electron doped cuprates, and we find the plasmons in both copper and oxygen ages in the electron doped case. So those things, I think, have to be studied in further detail. I mean,
Okay.
in fact, if you look at the oxygen cage,
in the interest of time, I have to cut the discussion here. Feel free to use the breakout room. You can continue the discussion in the breakout room, but we have to move on to the next lecture.
No problem. Thanks a lot.
Thanks.
All right. So thank you, Abhishek, once again. If you stop your presentation, is Phani Kumar, Dr. Phani Kumar here?
Zooms.
Yes, I'm here.
Yeah. Could you share your presentation?
Yes.
So now the next speaker is Dr. Phani Kumar Peddibhotla from IISER Bhopal, and he will talk about high resolution spectroscopy, again on single nitrogen vacancy centers coupled to intrinsic effective fields in diamond.
Okay.
Over to you, Phani.
Yeah. Okay. So thank you very much for the organizers for giving me an opportunity to present the work I have done during my postdoc and also after coming to IISER Bhopal. So I'm working as a faculty member at IISER Bhopal since almost 4 years. So
Phani, would you like to make it full screen?
Yes. Yeah, I hope it is. Yeah. Okay, so let me start with briefly describing about the basic properties of NVA defects in diamond. So although Dr. Praveen has already mentioned about it, but let me quickly recap. So as we know that diamond is an insulator, and there are many possible, there are actually many different kinds of defects in diamond. And the one particular defect which we are interested in is this so-called nitrogen vacancy defect in diamond. And we are interested because this has got very nice special properties, which I'm going to explain soon. So this NV defect is nothing but we have a nitrogen atom replacing one of the carbon atom, and it simultaneously also has a vacancy next to it. And so this NV center can exist in more than one charge state. And what we refer to as the NV center is the negatively charged NV center. So where this NV, where we have a neutral NV center, accepting a charge from the nearby donor. So this NV minus has got a spin of 1 because there are 2 unpaired electrons. So this defect behaves like a single atom trapped in a diamond lattice. So so there are two crucial there are two crucial properties of this NV center which makes it very relevant for applications and also fundamental research. Is that so these NV centers, they can be optically addressable even at the single defect level with a confocal microscope. So when we excite them with a green laser, they emit red photons. And as I already mentioned, it has a spin. So spin of S equal to 1, which means that there are 3 magnetic sublevels. So one very crucial property of this NV center is that the fluorescence of these NV centers depends on the spin state in which the NV center is present. So this can be used for measuring magnetic fields using electron spin resonance experiments. So the kind of diamond samples which we use in our lab are typically, they look like this as shown in this slide here. They are of 2 types typically. One is the natural and impure diamonds, which contain very high density of NV defects and nitrogen impurities. These nitrogen impurities are just the P1 centers, which Dr. Pavan was talking about. And we also have these ultra pure and colorless diamonds, which have very low density of NV defects and nitrogen impurities. So if you take one of these yellow samples, actually they get this color because of the large presence of nitrogen. So if you put this diamond sample in a confocal microscope, and if you take a confocal scan of a certain region of the sample, then you see these bright spots, and these are all the single fluorescent centers. So the optical setup we use that we send this laser light through an objective lens, and this will excite the NVs, and the fluorescence emitted by the NVs, which is in the red region, which is in the red wavelength region, is collected back through the same objective lens and sent to a single photon counting module. So, and we can probe the spin properties of these NV centers using a magnet and also a microwaves. So before I delve deep into the research that we have been doing, I want to emphasize that these diamond NV centers, they have emerged as a versatile research tool in several areas of physics. So if by incorporating this single NV center into a tip of a diamond cantilever, this can act like a scanning probe. And this scanning NV center can be used to measure magnetic fields with very high spatial resolution and also single electron spin sensitivity. It can measure magnetic fields from even a single electron spin under the appropriate conditions. So here in this picture, you see that on the bottom right here, like in this paper, they have imaged the very tiny magnetic fields which are emanating from a antiferromagnetic material. And also this diamond has also served as a platform for the observation of exotic many body states such as time crystals. And also these diamond NV centers are also room temperature qubits. So they have also found application in quantum computing and also quantum simulation applications. So let me start with explaining briefly about the energy level diagram of NV center. So we have a diamond which is a very large band gap insulator. So it has a band gap of around 5.5 electron volts. And the energy states of this NV center are within this band gap. So you have this ground state manifold, which is labeled by G, and we have the excited state manifold. These are the orbital states. And within that, each manifold, we also have these spin sublevels because this NV center has a spin of 1. And at zero magnetic field, though the MS equal plus or minus 1 sublevels, they are separated from MS equal to 0 state. by a, let me use a laser pointer. They are separated by this 2.87 gigahertz, and this is due to the spin-spin interactions. And when you apply a finite magnetic field, this MS equal plus or minus 1, they split, and so we can measure this G-man effect using optically detected electron spin resonance techniques. So we have here the 3 sublevels, so we can choose any of these 2 levels as a 2-level system, and then this makes it a qubit, and this makes it a qubit which can be optically initialized, and also the spin states can also be optically read out. And also we can also prepare any arbitrary superposition states of these qubit states using microwave pulses. So we have a, yeah, so we have a completely controllable single quantum system at room temperature with high coherence properties and long relaxation times. So now we want to use these qubit spectroscopy techniques to measure these changes in the spin levels due to the surrounding environment. This surrounding environment can be intrinsic to the diamond lattice, or also one can exert external fields such as external magnetic fields, electric fields, and so on. So, and this can be DC or AC also. So first let me start with, I have already explained how these qubit levels are, they undergo shifts due to the magnetic fields by virtue of the G-man interaction. So depending on the proximity of this NV center to the permanent magnet or to the magnetic fields, we see this G-man splitting. So in this way we can perform magnetometry with these NV centers, and so we know that the single electron magnetic susceptibility is around 28 megahertz per millitesla. So if you have 1 millitesla of magnetic field acting on the NV center, we have 56 megahertz splitting. So what makes these NV centers very special is that they have very high counts. Even from a single NV center, they have a very high contrast. You can see the clear, we can achieve very good signal to noise ratio. And by virtue of it, we can measure magnetic fields within very short averaging times. So having discussed about how we can measure magnetic fields, let me explain about how we can measure electric fields. So let me confine myself to the electric fields existing within the lattice for the rest of my talk. This diamond lattice can also have these static charges or fluctuating charges, so nearby these NV centers. So let's say that we have a point charge which is around 10 nanometers separated from this NV center. So it is like exert an electric field of around 3 volts per micrometer or so. And we have this, this is the magnetic field term, this is the G-man interaction term, and this is the Hamiltonian, this is the term in the Hamiltonian which describes the interaction of the NV center with the electric field. So the way we can understand about this Hamiltonian term is that when in the presence of zero electric field, we know that this NV center, they have got this trigonal symmetry, because the rotation by 120 degrees will preserve the symmetry of the NV center. But if you have some kind of electric field acting on the NV center, then the symmetry changes, and because of this broken symmetry, we get these terms in the Hamiltonian. That is a very crude and intuitive way of understanding this. So, and you can see that even if you have a charge of separated by 10 nanometers, the spin energy shift is only on the order of 500 kilohertz. This is much smaller compared to the magnetic susceptibilities we have seen in the previous slide. So it is essential that it becomes tricky and challenging to measure these small electric fields, although it has already been demonstrated even from a single charge. So most of my studies during my postdoc and also here in Bhopal is focused on how we can measure the stress response on these NV centers. So I talked about electric fields, and now I will talk about stress fields and how we can understand the interaction of stress fields existing within the diamond lattice on the NV center. So we have a diamond lattice. It can be intrinsically strained. Like, for example, if you take a polycrystalline diamond, it can be strained because of these grain boundaries, or you can actually mount this diamond sample in a diamond anvil cell and apply uniaxial stress or hydrostatic stress. Or for example, here you have this diamond cantilever. You can make diamond cantilevers by etching techniques. And
Phani, you have 3 minutes.
Okay. Yes. So here also we can probe the response of the stress fields acting on the NV center because of the strain exerted on the NV center, as you can see in this 110 plane, the symmetry is broken, and you can see that, for example, for the case of transfer strain, you see that there is an elongation of bonds, and correspondingly we have this term in the Hamiltonian, which is given by these parameters mx, my, and mz. But unlike the electric field, stress is a tensor, so we have to describe them by 6 parameters. And so during my postdoc, so we have done some detailed studies of the stress susceptibilities, and then we have obtained, we have measured them to be on the order of few kilohertz per megapascal. Again, you see the stress fields are also, I mean, they weakly change the response of the NV center. So although I have talked about how the now let me talk about how the stress fields and the electric fields they change the energy level spectrum. So as you would have noticed from the Hamiltonian form of the Hamiltonian terms, they both are part of the NV center in almost the same manner. So they can either shift the energy levels, which is denoted by pi parallel. This pi parallel can be either due to the electric field or due to the stress field, or they are a combination of both, or it can also give rise to splitting. So after coming here to Bhopal, we are trying to understand in much more detail about the stress fields which are intrinsic to various diamond samples. We want to perform some detailed studies so in order to obtain new insights, and which we have also obtained. So for example, we started investigating this polycrystalline diamond, which has the single NV centers. And here you see that this is the continuous wave ESR spectrum at 0 field, and we have this splitting and also this shift of the energy levels. And I would also like to mention that because the stress response and the electric field response are very small, we have to perform these experiments at 0 magnetic field. That is very crucial to measure the effects of this intrinsic effective fields in the diamond lattice. So if we perform a high resolution spectroscopy of this spectrum, we observe these four resonances. Initially, we were not sure how we understand these spectral dips, because this has not been observed by the community before or explained in the literature. So our aim is to understand these things. So first of all, we have turned to the single crystal diamond samples, which we know that they are very ultra pure. There is hardly any charges. They are very stress free. And then we have performed the high resolution spectrum, and we see that we have these 3 nice resonances which are equally spaced, and this is perfectly understood by the community. And this is because there is no effective field and so on. But now if we have this 0 field splitting hyperfine term, and then if you have this effective field term, and typically most of the samples, they have these very small effective fields. In such a case, only these central resonances, they get split and shifted, but the outer resonances, they are not perturbed. But in our case, what we have noticed is that because these samples have got very high stress on the order of hyperfine interaction, so we see that there is a widening of the gap between these 2 outer resonances also. So in this way, we can understand how this spectra is modified because of the presence of very large effective field, which has not been observed until now. And also you can see that there is also a transition imbalance. So if you see that this one has a larger contrast and this one has a smaller contrast, and there is an imbalance between the inner resonances and also due to the outer resonances. And this is because of the direction of the effective field, which is oriented perpendicular to the NV axis. We have also performed detailed studies of this, but I am not discussing here due to time constraints. And we have also confirmed that this PCD sample is mainly dominated by the stress fields. And we are also actually done more detailed investigation and found new insights, but we are currently preparing manuscript reporting this work. So I think with this, I would like to briefly end my talk here. So in summary, I have what I would like to emphasize is that we can use these NV sensors to measure electric fields due to charges, and also measure stresses, intrinsic and also magnetic fields, even on the order of nanotesla or so. So let me take this opportunity to thank my PhD students and BSMS students here, and also my former collaborators. And let me also thank the organizers for giving me
Thank you,
opportunity.
Phani, for the interesting talk. So now the session is open for questions. We have time for a question. Is there any question? Okay, I don't see any raised hands. So if there are no questions, then thank you, Phani, once again. And we come to the end of this session. And so the next session is at 2:30. We will have 2 talks in the next session. It's a short session of 1 hour. And after that, it will be immediately followed by the concluding session. So please join the concluding session, where we will take feedback from all the participants on how the conference went. We'll get your ideas about the future, and we'll make the announcements of the next QMAT 2022. Okay, so see you at 2:30.